If I took a thimbleful of air and I put it into a machine that can sort molecules and atoms by type, and I have such a machine, and I took 1,000,000 molecules, I would find 778,880 or so are nitrogen molecules, 2 nitrogen atoms stuck together. They make up the dominant component of our atmosphere. Another 208,700 would be oxygen atoms, stuck together in an oxygen molecule. That's the stuff we breathe. The third most abundant atom in our atmosphere is argon. That's a noble gas, so it doesn't participate in chemical reactions at all and can be safely ignored. But the next two are molecules, water vapor and carbon dioxide, both of which are crucial in this effect of trapping the infrared radiation trying to leave the surface. Water vapor is present at about 2,500 parts per million. I say about because, of course, there are humid days and there are dry days. Humid days correspond to more water vapor molecules in the atmosphere, dry days to fewer. Carbon dioxide is present at about 420 parts per million. 420 parts per million doesn't sound like a lot. Maybe we can just sort of safely ignore that. But carbon dioxide is very effective at blocking the escape of infrared light and therefore crucial in this blanketing effect of the atmosphere. Going down further, we find neon and helium and krypton, all noble gases which don't contribute to any chemistry in the atmosphere and therefore are largely ignorable, and a little bit of hydrogen, which as soon as it gets into the atmosphere escapes into space. But there are 4 other molecules that are also gases good at trapping this radiation, gases that we refer to in general as greenhouse gases. We call them greenhouse gases because that's the way a greenhouse works. It's got glass on the roof. The sunlight goes right through the glass. Glass is transparent. That's why you can see out your windows. But the glass is partially opaque to the outgoing infrared light. And so the sunlight comes in and warms the air in the greenhouse, and the infrared radiation which tries to escape is blocked. These 4 more greenhouse gases are methane. They're at just under 2 parts per million. Nitrous oxides, both from natural and man-made sources, at about 1 part per 3 million molecules. Ozone at a similar concentration, that's 3 oxygen atoms stuck together. And then chlorofluorocarbons, purely man-made chemicals that are in there at fractions of a part per billion, but are super effective at blocking outgoing radiation. So that's the composition of the air in this room. Does it change? Back in 1958, a geophysicist named Charles Keeling decided it would be interesting to attempt to measure the amount of carbon dioxide in the atmosphere. Since our atmosphere is very well mixed, it almost doesn't matter where you do this, and so he picked a nice location, the big island of Hawaii. And so since 1958, we've had on Mauna Loa an observatory which every day measures the number of carbon dioxide molecules per million atoms in the air. What Keeling found in his very first observations over the first couple of years, there was a clear annual cycle to the concentration of carbon dioxide. That in October, November, December, January, February, March, April, May, the amount of carbon dioxide steadily rose. And then in May, to June, to July, to August, September, October, the amount of carbon dioxide fell. What he was observing was the Earth breathing because it's covered with plants. What plants do is suck carbon dioxide out of the atmosphere, use energy from little packets of sunlight to break the bond between the carbon and the O2. They breathe the oxygen molecules back into the air. That's what we get to breathe. And the carbon is incorporated into the cellulose, the fructose, and the other molecules that make up plant material. So what happens in May? In May, the leaves come out on the trees, the grass all turns green, the flowers blossom in your garden, the corn grows in the field, and these plants get busy sucking carbon dioxide out of the air, breathing out oxygen, and making lots of plant material. The amount of carbon dioxide in the air steadily declines from May to June to July to August to September to October. Then what happens in October? Well, the leaves fall off the trees, the grass goes brown, the stalks of corn dry up in the field, the flowers all die, and the plants stop this process. But the bacteria have been waiting. Bacteria take the rotting plant life, take oxygen out of the air, combine it with the carbon in the plants, and breathe out CO2. And so from October to November to December to January to February to March to April to May, the amount of CO2 in the atmosphere goes back up. Now, if you've been listening carefully, you'll say, but wait, you told me that when it's winter in the northern hemisphere, it's summer in the southern hemisphere and vice versa, so shouldn't they cancel out? Well, you can answer that question by just looking at a globe. The amount of land mass covered with plants in the southern hemisphere is a small fraction of the amount of land mass covered by plants in the northern hemisphere. So it is true the southern hemisphere undergoes the alternative cycle, but the northern hemisphere completely dominates because it has many times more square miles of land in which plants are doing this photosynthesis routine. Over the first 3 years, this cycle was very clear in Keeling's data, but we've kept accumulating this data now for something like 70 years, and this is what we see. Those big oscillations up and down are now little tiny wiggles on a clear long-term trend. From 1958 up into 2000, the amount of carbon dioxide in the atmosphere has gone from an average of about 315 parts per million to about 370 parts per million. And if we go to the present, to 2021, it's now up to 419 parts per million. It's increased by 40%. That's the dominant trend. I had said that these different molecules have different effectiveness at trapping infrared radiation, and I wanted to briefly summarize that here. Methane is 26 times more effective than carbon dioxide, and nitrous oxides are more than 200 times more effective than carbon dioxide. So we have to take the number of molecules times their effectiveness to say what their net effect on the blanketing of the Earth is. And that's what's shown in the column of this table here. The carbon dioxide contributes about 1.88, methane about 0.49, nitrous oxides about 0.17, where the units here are watts per square meter. The Earth receives on average over day and night and over the seasons and over the latitudes about 340 watts per square meter. The extra gases we've added to the atmosphere increase that by about 1%. They don't increase the amount of energy coming in, but they decrease the amount of energy going out. And as a consequence, we've turned up the temperature. And you can see it's not just carbon dioxide. The carbon dioxide, the methane, the nitrous oxides have all been trending steadily upward. The only exception is the chlorofluorocarbons, which are very effective, but very rare because they're all man-produced. And you can see that CFC12 and CFC11 are going down with time, because back in the 1980s, we did the Montreal Protocol, in which, recognizing the destructive effect of the chlorofluorocarbons on the ozone layer, we decided that we should stop manufacturing them. And gradually, over decades, they will come out of the atmosphere and stop destroying the ozone and, in an ancillary point, stop warming the planet. So it is possible that international agreements can actually change our impact on the climate and the atmosphere. So everyone's seen this graph of rapidly growing carbon dioxide. Everybody knows that we've been adding CO2 to the air. But what most people don't recognize is that simultaneously, the amount of oxygen in the air, the stuff we breathe, has been going down. Here's a graph from 1990 up into the 2000s that shows the same annual cycle, but is trending downwards by about 19 parts per million per year. Now, not to worry, we're not going to run out of oxygen to breathe anytime soon, but as we need to understand the source of the CO2 rising in the atmosphere, we need to understand the reason for the O2 declining in the atmosphere. Where is it going? Possibly into CO2. In fact, there's a correlation between the amount of O2 leaving the atmosphere and the amount of carbon being added to the atmosphere. Correlation is important to investigate, but it doesn't indicate a cause. The circumstantial evidence that there's a connection here is that the mass of missing oxygen in the atmosphere is just about equal to the mass of the oxygen in the new CO2 molecules that have been added to the atmosphere. Burning things means combining them with oxygen. Burning fossil fuels means combining carbon with oxygen that ultimately make CO2.